recording. All right, welcome back everyone to PCB Design Fundamentals Part 2. So a couple of logistics things to discuss before we get started too far here, before we get started on today's slide. So as you heard me discussing with James a little bit here, so over the weekend between Kelly and I, we did our best to finish off everyone that either needed a license or needed us to send an alternate email. So I sent out a bulk email to everyone that was still waiting on that still looked like they needed to send an alternate email. I know several of you have replied back. It's like, oh, I already have an account. Here's the email I use. I just need to be added to the cloud. I will do those this evening. I know several of you have already replied back with here's an alternate email, but as you just heard in the discussion with James, the big issue that we run into, and Kelly and I have tried to explain this, but let me be a little bit more clear. If you go in, create a new alternate email address, and pre-register that email address with Altium, like creating the Altium Live account, we will not be able to add that to our license pool. So if I sent you an email saying we need an alternate email address, please just send us what that alternate email address is, and do not attempt to register with Altium. Do not attempt to request a trial license. Please let us add you to our license pool, at which time you will receive the email from Altium, which will already have your Altium account credentials where you'll just be able to log in. All right. So again, please, if you got that email from me, I saw that several of you have already replied yesterday and this morning. I will give those another try. But if you get another email from me saying we need yet another alternate email, please do not try to pre-register that account in Altium. Please wait until you receive the email from Altium indicating that you have the license from Altium for Altium from IPC. All right. With that, any questions on that before we get started? And I know I did see several of you that said, hey, I already have an Altium account, in which case I just need to add you to our workspace, which again, I'll be working on that throughout the day today, time permitting. But otherwise, everybody should now be added that can be added should be added to the license pool and or to the Altium workspace as necessary. All right, any questions on that before I get started on slides for today? All right, excellent. And any questions on the material I covered last week? No questions on the material I covered last week? Yes, great. CA. Oh, and Kelly has already taken care of it for us. So thank you very much, Kelly. The IPC corporate workspace account has now been renamed to IPC education workspace account. Thank you very much. Yes, Kelly, outstanding. And Kelly, did you have any other question besides the comment you put up in the chat for us?
No, not at all. Thanks, Chris.
Excellent. And thank you very much for taking care of that for us, Kelly, because yes, it was on my to-do list. I did not get a chance to do that over the weekend. Um, excellent, excellent. Thank you very much. So yeah, we've renamed that to the IPC education account just so that there will no longer be any confusion about that. All right. And for those that are relatively new to Altium, that did get your licenses last week, have you been able to download, install, and get through the walkthrough portion of the assignment? Getting familiar with that. Yes, no? All right. Well, guys, if there are no questions, let's go ahead and get started with this week's set of slides. Let me go over here. And let me put this up here and make this as big as I possibly can on the screen, which is not much bigger than it already is, but as big as I possibly can on my screen here. All right, so we're going to talk about some advanced layouts. There's not a lot of slides, but several of the slides we're going to spend quite a bit of time talking about today here. So we're going to talk about some of the more advanced concepts. Now, many of these routing concepts, we're going to cover in person some of the nuances of many of the nuances of routing we will talk about when we start working on our placement and routing and techniques we're going to use when we get into this week's assignment on Wednesday. All right, so placement-wise, when placing circuits, it is recommended to place high-frequency circuits as close to their connectors as possible, medium-frequency circuits next most close, and low-frequency circuits furthest from the connector. The intent is to limit the area of the board where high-frequency noise can exist. Other techniques can also be used to limit interaction of high-frequency and low-frequency circuits, and we'll talk about a few of those here in a minute. But, and I will describe a little bit here graphically in my scribble tool what the intent was here. I'll also pull up our IPC 2221 standard here and show you where this came from and what the intent was here with this discussion. Now, in modern board designs, this will be a little bit more difficult to implement as we are no longer doing card edge, but this did come historically from the card edge type of connections. Let me see if I still have 2221 available in here. It might be too far back. 6. Okay, yep, too far back. Let me go over here and not pull up that one. Meant to pull up the button next to it. Let me go up here to my Dropbox and open up my IPC 2221. Okay. Historically, when we were building card edge type of circuit boards here, right, that plugged into, chassis harnesses and so on with card edge connectors right here. The intent was that closest to where the connector fingers were, anything high frequency, medium frequency next, and low frequency next. And the idea with this, and I'll actually use, I'll just grab this and we can just draw in here for a second. Okay, so the idea was, sorry, I need to get my little stylus. The idea was that if I have very, very high frequency signals, that I want those to only go you know, let me do it this way. Let me just do pen. Right? I want my high frequency stuff to be down here in this area. Because if I allow my high frequency up here, and then coming back down here, and I have low or medium, that means that my low or medium frequency down here, if I'm trying to have sensitive DC down in this area, it means my high speed or high frequency signals are passing directly underneath it, which in turn is causing uh, my signals to have potential noise and coupling and other problems. So the idea was to keep the higher the frequency of the signal, keep it in a smaller contained area so it does not have the area to interact with medium and low frequency. So the idea was to keep the low frequency signals furthest away from the high frequency, or basically what we are trying to do is to isolate the high frequency and the medium frequency from the low frequency and so on. So that's the idea with it. Now, implementation wise, this is where the challenge comes in. And I'll explain that here in just a moment. Okay, and we'll actually see that more on, we'll see that more on Wednesday's class when we start doing some layout work here, but let's go back here and talk about this, for example, here. Okay. So we'll talk about a few of the do's and don'ts, but back to the intent of the high and the low frequency. So while we say we want to keep the high frequency as far away from our connectors as possible, that is a general statement. There are actually cases where we want the low frequency as closest to its connector as possible, especially in the case of low frequency, low voltage. And we will see a case of that on Wednesday, speaking of our pressure sensors, our pressure transducer signals that we have in our design. These are going to be very low voltage, say 20 millivolts full scale. It's going to be a linear DC voltage, so it's not going to be an AC voltage. And because it is such low voltage that now we have to be concerned with IR drops. And so in this case, we're going to put those as close to their connector, but we're going to put the connector and the circuit as close together as possible so that the entire uh, area is one small self-contained area. Some other do's and don'ts. Several of the key areas of board design that are quite often overlooked by the designers have to do actually with mechanical issues. One of the big ones, and this burned me more than once in my career, is blocking of tool access. Okay. For example, here, and I will freely admit, this is something, although at the time it was a recommended placement based off of electrical performance, what all of us, myself as well as the other engineers that worked on this design, failed to take into account was any rework. So for example, right here, we have these extruded heat sinks right here that are mounted to these vertical TO220 transistor packages. These happen to be linear voltage regulators in these housings here. This particular extruded heat sink had a pair of large diameter pins that could be soldered into the board to help further uh, transfer or dissipate the thermal energy into the structure of the board, namely internal return planes. The problem was these got pre-assembled as a sub-assembly, so you bolt you've got the heatsink material here, you've got the tab, you've got the screw with the lock washer right here. And the problem was once the board got assembled, these large diameter and tall height electrolytic capacitors blocked the ability to get a screwdriver in here to loosen this screw. So when one of these voltage regulators failed and needed to be replaced, the only way we were able to replace them, because now I have a heatsink in here, and while it's one thing for an assembly house with the major thermal energy capability of a reflow oven, along with you know, the reflow energy of a IR oven, plus any hot pots and preheaters and so on to be able to solder that heatsink into the board. Yeah, using a little hand soldering oven uh, was near impossible to remove that part. So the only way to actually remove the transistor was now to remove the capacitors in front of it. So every time we needed to replace a voltage regulator on that design, we ended up having to replace both of the capacitors in front of it just so we could get the screwdriver in there to remove the screw from the heatsink so we could unscrew the part, and then we could because we could desolder the pins of the part itself, but we could not desolder the pins of the heatsink. So do take tool access into account when working on your placement. A couple of other areas that are quite often overlooked in tool placement here. This is the other big one. So if you have your board here and you have your mount hole here, and let's assume you have some kind of hex nut that you need to tighten down to tighten this board onto, say, a standoff of some kind. Yes? Okay. Now you go in and you work out that the washer for this part is like this, for example. And so you go in and say, okay, based off of the 6 degrees of mechanical freedom, I should have a clearance that big around my part, right? Which basically means, in theory, from an electrical clearance point of view, I should be able to put my little surface mount resistor out here, yes? We'd all agree with that? That electrically, that should be fine, yes? We'd all hope.
Electrically
Electrically,
maybe, but mechanically you maybe
exactly.
will hit it
Yeah,
with the tool.
mechanically, the item to remember is the tool itself, right? Well, I said the 6 degrees of freedom. So this dark blue line around the outside here, that represents the 6 degrees of freedom of, the washer is off to one side and so on, the board's off to the other and so on. So that assumes that the physical parts that are in contact with the board, the washer, the nut, the screw, and everything else, will clear that surface mount resistor. The problem comes in is this, and let's go to the green color here. I have to have some kind of nut driver that's connected, basically a socket set, nut type driver. So this is the hex nut driver itself, the socket that has to go over the nut. And even though this tool, will not be present in the board after the assembly, during the assembly process, the body of that socket part might actually come down, and this has actually happened to me before as well. Not taking tools into account early on in my career and realizing that it's not enough to look at only the parts in contact with the board, the screw, the nut, the washer. also consider the socket head that has to go over the nut in order to tighten that nut down to the board. Now you have a more complete idea of the clearance around that mechanical hardware. So anytime you have mechanical hardware in your board, make sure you have tool access. A third situation I will describe for you that also happened in my career, which this one, thankfully, I caught before we built our first board and had discussion. So we had a relatively high power application. And ignore my poor drawing skills. We had an extruded aluminum heatsink right here. Had a couple of tabs out to the side. This bolted down to some housing here, right? Onto this, we had a pair of standoffs. Okay. And onto this, was mounted our circuit board. However, the reason we had this extruded aluminum heatsink is onto the heatsink, we had mounted a big IGBT module. Don't worry about what an IGBT is if you're not familiar with it. And its solder pins, it was a through hole, so its solder pins went up through our board. However, so far, so good. It also had to have its hardware here. That was drilled and tapped. Right? So we had our threaded fastener hardware to bolt these two mounting features into the onto the heatsink. However, if at any time this board needed to be replaced, we needed to be able to, after these are soldered. So the order of operation of assembly was first this IGBT module got bolted down onto the heatsink. The board got laid over it with open solder holes. Then we'd solder the pins in place. Now, however, in order to remove this from the heatsink, we needed to be able to have a tool get down here to these screws on the bottom. So what we ended up having to do was to have a pair of holes in the board. We had to have a couple of non-plated holes just so we could get our screwdriver or Torx driver bit down through the board to loosen up the threaded fasteners here. So again, whether directly or indirectly, it is incumbent on us to take tool access into account at all times, right? Consider not only the finished assembly as a whole, but consider the step-by-step assembly process as well as the disassembly process when you are working through some of the how you're going to do your placement, how you're going to do your board designs. Okay. Second one, human interface devices, or HID. Do leave proper clearance for human interface devices. On this particular board, and we'll see this board again when we get to signal integrity, we'll have further discussion on this back then. But over here, what we're going to see is that, yes, there is a question out there. Yes, Edson.
Oh, Chris, I agree exactly what you explained to us. And just one comment. It's very, very important all PCB designer be in contact with assembly process, manufacturing process, and testing and other teams working together, because it's maybe some information we don't know immediately when start the project, but it's very important to understand how the PCB will be assembled and the mechanical parts. It's very, very important.
Yes, thank you for your comment, Edson. Appreciate that. All right, so we'll see this board again, but here's the other side of that. Not only do we need to consider tool access, but we need to consider human interface. So in this example here, I have a board with a significant amount of open space. And that's because I have a number of mechanical switches here. This particular board itself was intended for elevator controls. This was from a elevator control system mounted in the machine room, up on the roof of the buildings, and so on. And we used to jokingly talk about the sausage finger size of our elevator contractors and technicians. The guys who move the big steel around, they naturally have big muscular fingers and hands and so on. And so therefore we would end up, uh, we needed to design the spacing both laterally and vertically and horizontally, the spacing between these, in such a way that a human, especially a human with a more robust, large, muscular frame and features and so on, could get in there and flip one switch at a time if necessary and not need to go in there with like a little pair of tweezers or something, right? So we ended up having to consider the spacing. So you'll notice significant amount of dead open space, both between the switches in this orientation as well as the switches in this orientation, so that after it was packaged in its housing, that there was still sufficient room for the human to interact and interfere and interface with it without having a significant mechanical interference between two or more of the switches, where you try to flip one and you end up, your finger catches on three of them at the same time. For anybody that's ever worked in digital and looked at those, the little 8-pin dip switches for settings inside a computer and so on, you're usually taking the tip of a ballpoint pen to flip one switch at a time because they're so close together, right? One human finger can't push them one at a time. We're trying to avoid the same kind of things here. So do consider human interface, and not just in mechanical things like switches and so on, but also in things like LEDs, lighting, displays, and so on. We want this to be a pleasant uh, interface and experience for the humans. Okay? Do's and don'ts. Labels, and again, for the human, right? If this is computer and AI based, we can just program the system and it'll do what we need it to do. For something like a human interface, in this case, this is a pluggable screw terminal. So this is a two-part screw terminal. Phoenix, Weidmuller, other brands that make these type of parts, where you have the actual screw terminal itself is in a plug that'll plug into these headers right here. So it becomes separable that way. But you also have it where we've got so many contacts in a row that if I rely just on a document that says location 1, connect the field wire for this signal to position 1 and this signal to position 2 and so on, it's very easy to get lost and confused and out of sequence and get things connected wrong. So taking the time to consider the end user that might have to do this, for example, uh, like the elevator technician who has to do the wiring for the building wiring or field wiring into the individual control boards with the wire harness, it's a good idea to consider adding in some kind of labeling to the board, whether that's in legend ink, labels, or the like. It is a good idea to do something like that right here. And so you can see we left room for labeling of the switch function here. Here's the dip switches I talked about, a few more of the connectors here, the backup battery, etc. So wherever possible, try to leave room on your board for human interface and wiring connections and so on. Don'ts. Tall, thin, fragile parts next to thick, round parts. Again, consider packaging and shipping and the effects those might have on your product here. as an example, here is another one from my own case, right? Electrically, we have, this is one of those poly resettable fuses, right? So basically those thermal fuses where the overcurrent event, this heats up, opens up until the short condition goes away, and then it resets itself. So you can see right here, we had this large, uh, rectifier diode right here behind the device right here. Electrically, this made sense. You can see the part right here. You can see how we had the part would stand up, and when placed in the final assembly, this would be fine. What we didn't take into account is this was this one tall part standing up right here. And what ended up happening was during shipping, the boards were all put in the boxes, even though they had the bubble wrap around them. Just the weight and bouncing of, going down the road, on the trucks, whatever you have it. They bounced enough, and this part rolled over the round part. And because of the nature of it, it basically rolled over and broke in half like that. Basically, just flexed past its breaking point. So again, this should be taken into account. Maybe try to reposition your circuits a little bit so that you can lay this guy down flat. Consider maybe some kind of staking compound or other mechanism of that nature. But yes, doing something like this, while electrically fine and in its final configuration, it's fine, not taking into account the ability to consider the intermediary step of shipping had a detrimental impact. This caused myself and 2 technicians and 2 other engineers, so a total of 5 of us. We spent 2 weeks replacing this. This was an order of 2,000 of these boards. So it took us a week to desolder every single one of these that broke and solder in replacement ones and so on. Okay, so again, don't place tall, thin parts, especially fragile, breakable parts like that, next to our short, round, fat parts like that. You'll get the bend over effect during shipping, unless it's properly taken into account. Any questions on some of these do's and don'ts of placement before we get going on other steps? Yes, no?
Hi, Chris. I've
Yes.
had surface mount parts that have had to be epoxied in place. Make sure there's space around those parts as well. Otherwise, the epoxy will go over the components and cover them completely.
Yep, I actually cover that in my military aerospace, and we call it staking. So where we're doing any kind of adhesive bonding, and yes, there's actually requirements in the J standard 001 workmanship standard, exactly to that point, that basically says clear the board space and make sure that the encapsulant or staking compound is not allowed to ever get on any of the solder pins or solder contact points. But yes, great point. Make sure you have enough sufficient room for the staking compound. That's not usually something I cover in this fundamentals, but that is a great point. Anything that needs to come in contact with the board surface, make sure you've allowed room for that in your design. Any other comments or questions? Great comment. Appreciate that. All right, if there's no other comments, I'll move on here. We will start talking about Manhattan length here. How many of you out there have heard this term before called Manhattan length in reference to design? Really? No one out there's heard the term in board design called the Manhattan length before? Alrighty then. Manhattan length is a term that has been around for a long while, from the early days of the board design, where early on we did not have the advanced routers we have nowadays. Instead, what we had were simple XY routers. All lines were either perfectly horizontal or perfectly vertical. And so in an effort to try to estimate what the total length of the copper would be before you went through all the trouble of laying out your board, you would estimate it using what we call the Manhattan length. We derive the name Manhattan from the city of Manhattan in New York, which is one of the first early cities in the United States that was laid out on a perfect XY grid system rather than traditional, roads and cart paths and so on. Instead, it was all the east-west roads are perfectly east-west on a grid, and all the north-south are perfectly north-south on a grid. So the way the Manhattan works, you can think of it as the opposite of the Pythagorean theorem. Who out there remembers Pythagorean's theorem about right-angled triangles? I know at least one person out there. Yes. What's Pythagorean's theorem?
So if you square both sides and then take and add them and take a square root of that, you get the length of the diagonal. Very badly translated to English.
Yes, exactly. In a right triangle, we have A, we have B, and we have C, which is C we call the hypotenuse. Excuse my writing, the hypotenuse or the diagonal, right? So he said, Pythagorean said that C squared was equal to A squared plus B squared, which goes to C, is equal to square root of A squared plus B squared, right? Okay, now, with Pythagorean's theorem, we're usually trying to solve for C. But in our CAD tool, in our ECAD tools, we're usually given C. C is that little rubber band connection line from the centroid of one pad to the centroid of another, and we're trying to go back and calculate the X distance and the Y distance. Now the tool can do that. It can say, I know the X1, Y1 and X2, Y2, so it can derive X2 minus X1 and Y2 minus Y1. So it can derive those force, but it's basically the reverse of Pythagorean. Instead of trying to calculate the length of the diagonal, we know the length of the diagonal. Instead, we want to calculate the total summation of the length of X plus the length of Y, and it'll report that as a estimated length of copper that will be in your design if you were to route this in a purely orthogonal XY method. Now, we know in modern routing, we very rarely get perfectly orthogonal. We will do our best to try to optimize our routing to favor orthogonal, but we rarely, if ever, will be perfectly orthogonal. We'll see what we mean by that moving forward here. Okay, so this is what we mean by the Manhattan length. Now, how is this going to help us? So what if I have a net that has multiple connections? So the previous page, my fictitious net had one connection from pad 1 to pad 2. Here I have a net that has 4 connections, 1, 2, 3, 4. So I have this rubber band, I have this rubber band, and I have this. I have 3. I have 3 X distances and 3 Y distances. Okay. So again, the Manhattan length is going to be used to estimate the trace length. It'll be determined by adding all of the delta X and all the delta Y dimensions between the nodes of the given net, like we see right here. Most CAD tools, Altium, Cadence, Mentor, KiCad, and the like, have a tool somewhere in them that reports what the Manhattan length of a given net will be. In Altium, it's in a panel called the PCB panel, and in there is a pull down for nets, and in there we will see what that is. Now, where the Manhattan length is going to help us, again, since it is an estimate of the unrouted length, we can use the Manhattan length as kind of a helper to tell us what nets we should be working on for our routing as we're working on routing. So if I have a fairly large board to route, I'm going to start looking at Manhattans. If I have a net in there that only has like 10 mils left to route, I'm going to go seek that net out and just route it to completion, call it done, before I start working on the net that's got, 1.274 inches left to route, and so on. And again, measuring the distances here is an estimate that I did based off of these. I did the 3 measurements. For the 3 X's, I rounded up to the nearest 5 mil, and for the 3 Y's, I used the exact rounding value here. Interestingly, the decimal values worked out perfectly, and you can see I'm about 200 mils delta here, just because of my rounding on X that I did right here, as opposed to my explicit numbers right here, but you can see how close I was. 1074.622 versus 1274.622 reported by the tool. And again, I'm simply going to measure the delta X, delta Y here, delta X, delta Y here, and so on. Okay. Okay, any questions on Manhattan length and trace length estimation? Now, one other thing I'll comment on that Manhattan length, as we route nets to completion, right? As you are working on your routing in the design, what you're going to see happen is that these nets will start, the Manhattan length will start decreasing, and the actual routed length that's reported over here will increase. So our goal is to get the routed length to whatever total length we have and to get our Manhattan length to 0. One last caveat on Manhattan length with most tools here. Because the original concept of Manhattan length was developed in the early days of PCB design and layout, it was developed before, even back when we were doing single layer boards, before we did multi-layer board design. The main problem that most CAD tools have with the Manhattan length estimation is it does not take Z-axis into account. I actually got burned on this early on in my career. Call this 30 years ago now, 1992 time frame. And one of my very first boards I did, I was only using the Manhattan length tool, and Manhattan said every trace was routed to completion. But what happens if one part is on top and the other part I flip completely to the bottom, right? Imagine I took this resistor right here, flipped it to the bottom, and positioned it such that this pad was directly underneath this pad. So the total delta X and delta Y between these two pads was 0. It was completely Z-axis delta. So even though I had neglected to drop the via that connected the top side to the bottom side for these two, Manhattan length still reported it as 0. So I inadvertently thought that my board was routed to completion, even though it wasn't. Now, I will say there are newer tools, and I'll demonstrate those time permitting, called DRC check tools, which will allow us to actually check for full complete routes, and it will take Z-axis into account. But the classic Manhattan length tools will miss Z-axis because it's only looking for delta X, delta Y. It's a 2-dimensional tool, not a 3-dimensional tool. All right. That's the last thing I'm going to say on that. So any last comments or thoughts on Manhattan length before I move on to the next subject?
So maybe just one comment or question. So, but basically Manhattan length then, let's say it severely depends on the component placement, right? And that means that, so generally, or maybe I was doing it wrong, but generally for me, it is kind of an iterative process where kind of components are moved and then partially routed, and then let's say you kind of move the components around. So I'm really wondering if now in modern times Manhattan length has any practical application that we can benefit from.
Yes, it still has a practical application. And so even if you move the parts around, the Manhattan length will update. And again, I actually still use Manhattan length myself because it is a good, since all it is an estimate of length to be routed. Any net that I see in my list here that says it has any Manhattan length to the net at all, it means part of that net is not routed. So I can then select that net, highlight it, go look for where I see a rubber band or so on, and know what nets I need to work on. So it helps me order, and we'll talk about this when we get into the layout, but it helps me in how I work on my design. Usually what I do with my design, after I've got all of my parts placed, I do what I call pre-routing with the little sub-circuit pieces. I get all the sub-circuits placed, and then I'm starting to work on my board. But typically what I end up doing is I take a quadrant of the board. Like I'm just going to work in the lower right-hand corner of my board today. I'd try to route that whole corner to completion as best as I can, right? And so on. And so by doing that, I'm going to use the Manhattan, and that's going to help me know if the nets in that area of my board have routed to completion and so on. So yes, the Manhattan does still have some benefit because it is going to be a guide or aid to tell us if nets on our board still need any routing before we do our final DRC check to make sure we got all of our Z-axis as well.
What would
Thank
be
you.
what would be the benefit of using the Manhattan versus just doing a DRC?
The Manhattan is live updating as you're working on it. The
Okay.
DRC, you have to stop, pause, run the report, read the report, sort by net. One of the other things that the Manhattan, and I'm going to speak specifically to the Altium tool right now. I believe Cadence and Mentor have a similar behavior. But with Altium, I can also go in, as you saw in this image right here. See how it says net is hidden?
Yeah.
Right? I can go in here with this nets view and say, oh, I just want to look at my 32-bit memory bus. Let me hide all the other nets for now and just look at my memory bus for now. Or I want to look at my power nets, or I want to look at this group and so on. So I can also restrict which ones I'm looking at by group. I can sort by Manhattan length, by fully routed length, and so on. So by having that there as a real-time live updating aid, it's going to help me know where to focus my attention while I'm routing versus pausing and having to run a DRC report over the whole board and checking things that way. If that makes a little bit more sense.
Yep.
Cool. Great question. Any other questions before I move on? Okay. Now we're going to start talking about multi-layer routing. Okay. Due to the non-uniform structure of the copper surfaces needed to ensure the resin bonding, the potential exists for voltage arcs depending on our dielectric weave we've chosen. Now, more on this when we get to materials later, but we talked a little bit about this with Stackup last week. But beyond that, we'll get to this more later. What we're going to find is that all of our dielectric materials, specifically the board layers, between the glass and the resin itself and the copper, right, we have to roughen up the surface of the copper in order for the resin of the glass and the glass weave material to have bonding to actually occur. More on that in materials. We're going to have these min and max peaks right here. And the minimum is a peak to a peak. The maximum is a valley to a valley right here. We care about the peak to the peak. Now, here's the big problem. If two of these spikes, say this spike right here and this spike right here, happen to line up with each other in X and Y, and this is going to be a double-edged sword that we will talk about more going forward. But from an electrical performance point of view and signal integrity point of view, we're going to see that we're going to want the higher resin content, which is also going to mean the thinner dielectric layers. However, the glass weave pattern in the thinner dielectric layers has less glass in it. And what we're going to find is that when we actually look at the woven sheets of glass, they are not uniformly full. We actually have these little holes between the weave patterns. More on that related to textile industry, more on that later in materials. But if you have the condition where you have two spikes that have lined up with each other, and those two spikes line up with one of these holes right here in the glass weave pattern, you have the potential exist for an AC or just a DC even, a voltage spike to happen, where the spike, you can have an arc over event happening, right? Where if you have a sufficient voltage, it can arc through the dielectric because you don't have the higher performance or higher insulation of the glass material. You only have the resin material, and you can actually have a arc over event happen that can actually cause some problems. The preference is going to be to select newer weave styles that spread the weaves smoother to minimize. More on that in material section. The other preference is going to be to have a minimum of 2 sheets of prepreg per layer if you are designing for high reliability applications. If you're going for low cost, you might still use the single thin dielectric and just live with the risk that you might have this intermittent arc over event happening. Okay, more on that layer. Now, the second issue, so that leads us into Stackup. And actually, I think this is a great place to take our break because we're going to be talking about Stackup. Some, I don't want to say controversial, but some topics that are not normally spoken about the way I'm going to describe them here. So why don't we take let's call it 15 minutes, be back at the 10-minute mark. I will stay online if there are any questions, but let's take our break here, and then we'll come back and we'll talk about the various different stackups, what happens with unbalanced z-axis, layer ordering, and so on. And we'll go from there. Right, so 15 minutes, bio break, caffeine break. Be back at the 10-minute mark, 10 minutes after the hour. All right, so everybody back from break?
Yep.
All right. Actually, excellent. Let's continue on.
Yes,
Excellent.
I'm here.
Excellent. Excellent. Okay, the next topic we're going to talk about is in our Stackup. It's what I call z-axis balancing or z-axis mirroring, meaning that number one, in a standard multi-layer board design, we always, and I do mean always, want to have an even number of layers, okay? Second, when you have an even number of layers, we want to find what we call the z-axis midline, which will be the dielectric layer between the top half of the copper layers and the bottom half. So in this case, we have a 10-layer board that you see right here. Right here, we have 5 layers of copper above, 5 layers of copper below. So this dielectric layer right here is a z-axis midline. The idea is I should be able to, if I were to print this on paper, right? If I was able to print this piece of paper in half, I should be able to fold it in half along this midline point here. And I should have both the layer type definition and the copper weight definition, as well as the distance. And I should say that. I should say it this way, comma, copper weight definition. Okay, so the copper type, weight, and layer separation should all be mirrored. Meaning, if this layer, if the copper layer directly above the axis midline is defined as a signal type layer, meaning I'm intending to route on it, the layer below midline should be a signal layer. If the distance separate whatever, now these are okay because this is by definition going to be uniform because I've got, one dielectric thickness, so the z-axis midline is exactly half. But for all others, so between this layer and this layer, if this is 10 mils of prepreg or 5 mils of prepreg here, this should be 5 mils of prepreg here. If this is a plane layer, this should be a plane layer, and so on. So basically, I want not only my copper type, so this is a plane, so this should be a plane. If this is 2 ounce, this should be 2 ounce. If this is 2 ounce, this is 2. If this is 5, and so on. So I want my thickness, my type, and my distance from z-axis midline to be exactly mirrored both above and below the z-axis midline. Okay. The reason I want this is we'll take a look at a nearly identical midline. We'll take a look at a nearly identical stack up here. Same number of layers, same copper weights. The only difference is the distribution and layer separations here. In this case, here's my z-axis midline, but in this one, I have 5 of my 6 signal layers above midline. I have all 4 of my plane layers below midline, and then a signal layer on the bottom, of course. And what happens here is due to the physics of expansion and contraction. Does everybody out there remember back from science classes, physics, chemistry classes, and so on in primary school, secondary school, high school, college, university, etc. The idea of rates of expansion and contraction are different between different materials based off of thermal conductivities. Yes? Sort of? We all remember that? Yep. Okay, so conductive materials, metals like the copper in our board, are going to conduct thermal energy at a much faster rate, which means they're also going to heat and cool at a much faster rate. Otherwise, expand and contract at a much faster rate than, say, a polymeric material such as the epoxy resin and the glass, right? So an amorphous polymer material like the glass and resin of the dielectric layers is going to expand and contract or heat and cool at slower rates than the copper will. Yes? We all agree with that?
Yeah.
Okay, so now let's assume for a moment that during the heating process, say fabrication or assembly process, that all the layers are heated up uniformly and then cooled in a controlled method, right? My board won't see any problems. But during the assembly process, that's like during the fabrication process, but during the assembly process, for example, where I simply heat the board up and then after the soldering process, I allow it to cool, but without any kind of mechanical restraining the way I have in the fabrication process. More on that when we get to fabrication. What's going to end up potentially happening here is if I allow a stack up like the one we just saw right there, and I'm just going to draw 4 layers here. Okay. I'm going to have a solid copper layer here, a solid copper layer here, a signal copper layer here, and a signal copper layer here. Okay. During the heating process, these two are going to expand much, much faster than these two. These are going to have a much smaller expansion because there's not a lot of copper on these layers. Okay, we all agree with that, yes? The 2 solid plane layers are going to expand at a faster rate than the 2 broken copper layers of the signal layers. We'd all agree with that, yes? During the fabrication and the assembly process. Does anybody not agree with how I drew that? Okay, I'm going to assume everybody agrees with that. Now, what's going to happen here is the reverse is also going to be true. After I get to the soldering temperature, I'm going to go through the cooling process. Now, during the cooling process, there's no restraining mechanism, right? During the fabrication process, I'm in a clamped, I'm in a hydraulic press with pressure plates and so on, holding the board so it can't warp. But during the assembly process, after I get up to the soldering temperature and I start cooling, these 2 bottom layers are going to cool and contract in on themselves at a faster rate. So the forces pulling this now softened material in are going to be much greater on those 2 bottom layers. And because these 2 layers are going to contract at both a faster rate and a greater distance than the 2 on the top, what ends up happening is my board shape, when all is said and done, instead of being straight like this, ends up warping because these 2 bottom layers, because of the differences in the forces pulling in from the outside, are unbalanced. The 2 bottom layers contract faster, so I have a shorter distance on the bottom and this longer distance on the top, causing my board to arc or bow, twist, warp, etc. And so while electrically this might seem like a good thing, I've put all of my layers together right here. I've put all of my planes together. I get better planar capacitance, whatever the case is, right? The reality is that when you lead to an unbalanced z-axis stack up like this, during the assembly and other temperature excursions, this bottom half will expand and contract faster than this top half, leading to potential deformation of the board. Whereas this version right here, I have the exactly equal forces both above and below. So while I've got faster expansion contraction because I've got the same amount of force pulling against the top half as I have against the bottom, it's going to have a uniform expansion contraction, meaning I will mitigate the warpage problem. I'll still have expansion contraction to deal with, but I won't have the physical damage or warpage, bowing, and twisting effects that I have over here. Does that make sense to everyone what I'm talking about with this, with the expansion contractions right here? Yes?
Yes.
Okay, so this is bad. This is good. Okay. The next biggest issue we're going to talk about. So we talked right at the beginning of the class about this idea of putting my high speed close to my connectors, medium speed next, slow speed furthest away. The whole point of what we're trying to do with that is what we're calling current steering, or at least I'm coining that term, current steering. There's other ways we can do this as well. Effectively, we're trying to keep the low speed analog type of currents away from the high switching digital type of signals, or high power switching like we would for motors and other features of that nature. One of the ways we can control that, if we are not able to physically isolate, as I said previously, and say I have all of my connectors on one edge of the board, so I'm going to put all of my high speed first, then my medium speed, then my slow speed, and deal with my routing that way, right? And we'll get back to that in a minute, talk about physical isolation. But we can also talk about that by simply controlling the current by using a cut in the plane. Now I'm going to have, when we get to signal integrity, I've got a better graphic of this, more explicit graphic of this. But let's say, for example, this block of circuitry right here was some sensitive analog circuitry. And let's say, for example, I have some standard digital circuitry. Hopefully we're all aware of the fact that digital is actually high frequency circuitry, whether we meant it to or not, right? High speed switching, right? I should ask that, is anybody out there not comfortable with the idea that whenever I have a digital circuit of square wave, regardless of the clock frequency I'm running at, that I have significantly higher frequency content because of the nature that it's a square wave? If not, we'll come back to that when we get to signal integrity in a few weeks, and so on. But suffice it to say, over here, let's say I have some digital circuitry here, and this is my processor device right here, which say has A to D input in this lower right-hand corner. Let's just assume for a moment that I have A to D input in this lower right-hand corner. If I put a simple cut in my plane layer right here, I've now made effectively a little island. It's still a common return area out here, but I have now made myself an isolated area here where this analog circuitry can route analog path into the A to D area right here. The digital will route up here, over and across up into the digital area right here. And this digital signals should not interact with these analog signals right here because of this cut in the plane. Current always wants to follow the path of least impedance, meaning the shortest path it can possibly flow in. A physical cut in the plane, meaning removal of the copper here, says that that current cannot arc across this boundary here and must flow up around the outside. Once that current gets to this point right here, its shortest direct path to where it wants to go is straight to these pins right here. So there's no way that current is going to make a 180-degree turn, flow into this area only to try and flow its way back up here. That is a higher impedance, longer distance path, and it simply will not do that. So when we understand the physics of how currents flow, we will see that that current, by putting this simple cut right here, I can isolate my sensitive analog areas from my noisy digital areas here and still have everything perform as inspected. We do need to ensure, however, if we're going to go this route of using a cut in a plane like that, we do need to ensure that that cut or isolations exist on all layers, right? If I have, say, multiple layers of return and I only put the cut on the first return layer, it defeats the purpose because that current will simply flow on the second return layer underneath here. So we do need to ensure that those cuts or isolations do exist on all layers. That's one way we can deal with it. The other way we can deal with current steering here is in the case where I have a condition, if for whatever reason I need to cross from one return domain into the other without actually extending the domain into that area. So for example, let's say down here in the bottom half of my board, I have high voltage, isolated high voltage return, so some high voltage motor switching or something of that nature. But let's say for my motor drivers themselves, I need to bring my digital signal into this area, but for whatever reason, I can't just move my digital return plane down here for whatever reason. But this is a worst case condition here, you know, option of last resort, whatever the case is right here. But we can use, what we can do, oh, and I just realized that slide is wrong. That's the same current steering slide. But we'll talk about this option over here, is we can extend a trace from a signal trace from the common area up here across the boundary. And what we're going to do is use two signal layers, right? So what we'll do here is this. We'll use to extend across the isolation boundary. Okay. We'll say right. Whoa, didn't mean to do that. We will ensure boundary and ensure isolations are on all layers. So effectively what I'm doing right here is underneath this area right here, I'm going to make sure there's a cut in my plane layers, and I won't route any of my high voltage across this area right here. And what I've done, rather than extending the planes themselves into this area, I'm going to attach on two adjacent signal layers. One of the layers is going to contain the return path. I'm simply going to make it a finger of return that can go down in this area. And on the second adjacent layer, I'm going to make my signals right here, say these blue ones right here. So I'm basically mimicking the transmission line structure that I have up in this area while being able to extend into this area. For example, if these are my high voltage motor drivers here, and for whatever reason, they had to be mounted in this location. And this does happen occasionally, especially when it comes to things like large body parts where there's certain mechanical structural reasons why that particular part has to be mounted in a certain area. Say maybe you need to have the enclosure lid come down and make contact with the surface of it to act as a heat sink for some reason, that you can't just take this part, rotate it, and have it straddle the isolation boundary. So its digital input pins are on the digital side and its analog output pins are on the analog side, and so on. There are occasions where you'll need to do something like this. However, normally we're going to try to isolate, or straddle the isolation boundaries and not do something like this. But I have had cases where this was the only option to bring the digital signals into the analog area when we are using these isolated return. One of the best ways, however, we're going to control our noise and our current steering and so on is simple circuit isolation. Again, looking at the board as a whole, we have analog circuits in one area right here. We have digital circuits in another. We have the split boundary right here that says we're going to have our area right here. We're going to have our power supply generation, such as our voltage regulation circuitry right here. We're going to have that over here. And so we'll have all of that done like this. And we'll simply have this isolation boundary, and we'll maintain analog in the analog area, digital in the digital area. And we'll have not only XY axis isolation, but also Z axis. One of the biggest mistakes I see designers make is they have all of the sensitive analog circuitry and immediately put their digital circuitry on the bottom side of the board directly underneath it. While the plane layers should act as shielding, we have to take capacitive coupling into account because we're going to make capacitors out of our planes for high-speed switching signals that we're going to see here moving forward. Any noise that gets on those capacitors, high frequency noise from the digital switching, can actually capacitively couple through those capacitors into the adjacent signal layers. So we want to make sure that we ensure X, Y, and Z axis three-dimensional isolation, put the digital in the digital area, the analog in the analog area, and spacing is going to be one of our best deterrents or solutions for any kind of noise and crosstalk problems we might have. Okay, we're going to use external layers primarily for analog and power routing. The external layers are also going to be used for our escape routing out of SMT pads, and we'll try to use our internal layers for our digital signals. Internal layers should be routed orthogonal on adjacent layers to minimize crosstalk and other signal integrity issues. Meaning, if I have two adjacent signal layers, such as these two right here, these two layers are what we call adjacent layers, meaning the two signal layers are directly next to each other and they're separated from other signal layers by our plane layers that are going to act as our signals. So these two are orthogonal, these two are adjacent, these two are adjacent, and these two are adjacent. We're going to focus on these two internal layers here for this discussion right here. And what we're going to try to do is have one of those two layers be designated as our primarily horizontal layer and the other layer as our primarily vertical layer. In this case, my brown layer is primarily horizontal, my blue layer is primarily vertical. This is going to do a couple of things for us. Anytime a blue signal crosses a brown signal, such as in this little area right here, we'll notice that the actual amount of overlap is this very, very small area. That's the indicated crossover point. The amount of both capacitive coupling and inductive coupling in that area is going to be very, very small, minimizing the amount of potential crosstalk or coupling that might happen. This minimizes capacitance, capacitance between layers, which minimizes noise from capacitive coupling. This figure in 2221b, figure 6.7 shows the example. The other benefit we're going to have from having layers designated primarily horizontal and primarily vertical is it also is going to mitigate the possibility of us routing ourselves into a corner. I'm sure we've all heard the expression painting yourself into a corner. If anybody's ever painted their house or painted a room, painted floors or anything like that. You ever get yourself stuck? You're starting painting and you're going backwards and you realize you're in the corner of the room and you can't walk out till the paint dries. Probably all seen that in movies, heard that joke before, yes?
Sure.
Sure. The same thing happens on our board when we're routing. While it's possible, it's physically possible, say on this brown layer here, to route the signal from over here and route it up here to brown. Same thing, up and around to brown, and so on. But what happens if I have another signal on brown that needs to go from here, but cross past this point and get up to this point? I have no way through now. By having these layers, one is primarily horizontal, one is primarily vertical, I can simply push these, I can nudge these traces side to side a little bit to make what we call routing channels. So I will always be able to get one more signal through that area. Find my clean spot right here. You will be surprised how many, engineers, designers, and drafters I've talked to out there, reviewed, consulted with, whatever you want to call it, where I've still found them routing themselves into corners and then coming back going, oh, I can't get this one last trace through. And I say, well, let's cut all these out. Let's move these all to another layer. And now you can get through that area. So this could potentially be a problem. While it does require the use of extra vias, the ability to allow us to route in higher and higher density circuits definitely gives us the edge in being able to successfully route our boards to completion if we follow the orthogonal design right here. It also limits the ability of us to create antennas on our board. The more and more where I have these big looping paths where I go out, up, and back, the more and more I start to look like C-ring antennas, dipole antennas, and so on, versus I'm going to have just a straight line here, a straight line here on an adjacent layer. This is going to help give us a little bit of break to our structure, and so on. So for multiple reasons, we want to define on any two adjacent layers, one layer being primarily horizontal, the other layer being primarily vertical. Yes, question there from Mattia.
Question actually, how much of an impact do vias have for final pricing in today's, let's say, manufacturing process?
Nearly zero. So as
Mhm.
long as you are staying in within the manufacturing capabilities of your fabricator, and we will talk about those when we get to manufacturing week. But as long as you are under your aspect ratio limit, it's nearly zero. It used to be a significantly higher cost, but now as long as you are in a within the aspect ratio, the machines are so automated, they just load enough drill bits that they can drill all the holes. So it's I have not seen a significant cost adder for vias in a long, long time. Now, if you start doing blind and buried vias, laser micro vias, which is all in my advanced design concepts class, or if you start trying to exceed the aspect ratio, like the fabricator says, their maximum for standard is 10:1, and you've got your design with 12:1 or 15:1 aspect ratio, then there's going to be a cost adder. But as long as you stay within the fabrication capability limits, I have seen nearly zero cost adder anymore. It's
Okay,
so
cool.
automated nowadays.
Thanks
Great,
for the
great
reply,
question.
because that's actually something which was kind of pushing me in the corner, because I was always trying to fit as much as possible, let's say it on 2 layers or
Mhm.
or on 4 layers without using this orthogonal routing in a sense to kind of reduce the number of files that I need. But okay, since that is now outdated, I'm going to change that practice. Thank you.
Excellent. Good call. Excellent, excellent comment there, Mattia. Mm. Mm. Sorry. Okay. Sorry. Need to click over here before I push the page down. Okay. The next topic to discuss here is thermal designs or thermal tie designs. Thermal ties are used to prevent poor solder connections, such as cold solder joints, when connecting to large copper areas. So you're going to see we're going to start using copper pores in these big copper plane areas like we just talked about for our power distribution needs. However, once I have a very large copper area, which we just talked about, it's a very good thermal conductor. Now I'm trying to put thermal energy in to create a solder joint. Well, if the thermal energy I'm putting in is getting taken out faster than I can put it in, I'm not going to get good thermal performance and good wetting of my solder joint. So what we try to do is to create what we call a thermal tie. It provides a gap and a thermal impedance to allow localized heating of the pad. So if I have a through-hole or surface mount pad, instead of having a solid connection to the surrounding copper, I'm going to have these slight air gaps in here, and then I'm going to have these 4 thermal spokes right here, which are going to allow me to have the thermal connection I need, to have the electrical connection I need, while also having enough of a thermal impedance here to where I can get the localized heating of the solder pad while still maintaining my electrical performance. IPC 2222 is going to, or the other sectional standards. For this course, we're going to focus on 2222, which is the sectional standard for rigid multi-layer boards. If we're doing flex boards, it'll be 2223. If we're doing sequential lamination with HDI, it'll be 2226, RF 2228, and so on. But in this case, we will refer to our 2222 for the requirements for the design of the thermal ties. For vias, as Mattia just brought up, vias we don't normally associate with needing to solder to those. So for the case of a via, it is recommended to make those a direct connect, meaning make the vias have full 360-degree perimeter of their plated barrel hole as a direct connection to the copper pore area or plane area here. Okay, so we'll use direct connect. For the thermal ties, we can have either 45 degree or 90 degrees. So we can have the thermal tie offset 45 degrees or directly in line 90 degrees to the pad itself. 45 is going to be the preferred for high density areas. More on that. We'll remind me on Wednesday, and I will show you a demonstration of the difference between the 45 and the 90 in a high density area and how that would affect us. We can also be 2-spoke or 4-spoke, with 4-spoke being the most common. The total width of the spokes right here should be between 60% minimum and 80% preferred of the pad diameter. Now, for the copper pad, for solder pads right here, it's a little bit different. It's simply going to be, we'll get into that later, but for a traditional plated through hole, we're simply going to take the diameter of the pad, assuming we've designed the pad at the minimum necessary diameter for the fabrication and manufacturing. So from our IPC 2222, there is a set of calculations here. The first one is the land size calculation. This is also covered in 2221 in calculating the hole size and the land size and so on. But basically the land size should take the annular ring, so 2 annular rings to calculate that, take the fabrication allowance, and take, if the hole size, the maximum hole size determined from 2221, you take the hole size plus 2 annular rings plus the fabrication allowance, you add that all together and you get the pad size. So in 2221, it's A plus 2B plus C. There's a newer version of that calculation, and I've got to get myself a copy of that, which adds an additional modifier in there. But for the purposes of this, we can stick with the A plus 2B plus C. More on that on Wednesday, in which case we calculate this. Then for the thermal relief, we're going to start with a standard 60% right here minimum. So we take 60% of this calculated size right here, so 0.6 times that. We times our 1.35, we get our 0.8 millimeter right here. And then we simply divide that number by the number of spokes. So for 4 spokes, each one of the spokes should be 1/4 of that value right there. So we get 0.2. So each one of the spokes should be 0.2 millimeters, which is 8 mils. I usually just round up to 10 mils just from a manufacturing point of view. So I've got a little bit of margin there. And then if the actual land diameter chosen is greater than the minimum calculated, the percentage difference between the land diameters shall be subtracted from the total web. So let's say the calculation up here says the minimum should be 1.35 millimeters, but we actually made a 1.7 millimeter diameter land. Then we would say 1.7 minus 1.35 divided by 1.35 is a 25% margin. So we would take that same calculation right here, 0.8 millimeters minus our 25% of that, and we get our calculation right here. So we get 0.8 minus 25% of 0.8, just 0.035 minus 25% of that, gives us a 0.6 millimeter total, reduced by 25%. And we would then adjust our web based off of the width reduction right here. So basically, we always want our web based off of the minimum land size diameter that we would calculate using the calculation above. And otherwise, we would go in and do it this way right here. Okay. Last thing we're going to talk about here is differential routing. If we remember our right-hand rule from physics classes or electromagnetics classes, let's assume that the circle on the left, the solid black circle, is current is flowing out of the screen towards you, the observer. If you put your right hand with your thumb pointing away from the screen, you notice the fingers of your right hand tend to curl in a counterclockwise direction. around that wire. Now, if the second wire is flowing into the screen, that's our return path, so the current is flowing opposite direction, equal polarity. I point my thumb at the screen and will notice that the thumbs of my right hand now wrap in a clockwise. So I have one magnetic field. So the fingers of the right hand describe the magnetic field. The field of the signal coming out of the screen is rotating counterclockwise. The field flowing into the screen is rotating clockwise, and where those two fields meet, there'll be equal magnitude, opposite polarity, and so they will tend to cancel each other out. So differential routing is used to route differential signals. These are used for signals that transition from one voltage domain to another. Impedance is controlled by standard structures and the gap distance between the traces. All features, including vias, are equal and opposite distance from each other. Signal on one trace is the outgoing signal and the other trace is the return signal. Can also be both outgoing, where one is positive and one is negative, in the case of like RS-232 or RS-485. And either way, we have the two fields are opposite polarity to each other. And in this case, the magnetic fields are equal and opposite, and they will approximately cancel each other out. This in turn will allow us, when we're routing our traces, if we have a differential pair defined, as we will in our design, we'll be able to route, and we'll notice that the gaps are minimized, the via placement is equal and opposite, and the tool will do its best to attempt to maintain the equal and opposite gapping, exiting out of the vias towards each other, maintain this defined gap, and this will allow us to route and maintain our controlled impedance even if we no longer have the reference plane or mirror plane to act as the reference. This will allow us to route across our voltage domains, meaning if I have to leave one board, go across a cable harness of some kind, go into another board, and yet I still want my two signals to be equally and faithfully reproduced, I can do them using differential. So the vias are uniformly distant from the traces. Traces are routed with uniform width and gap, and traces will route closer to the pads and vias before separating compared to traditional routing techniques we see. The final thing we're going to talk about here, and we've talked about a little bit previously, but is the serpentine routing. The serpentine routing is used in digital routing to ensure proper signal levels arrive at the receiver at the same time. This is called serpentine, sometimes called accordion routing, sometimes called trombone routing, matched length routing, and so on. Classic was serpentine just because it snakes back and forth and back and forth, so on. The total length of trace determines the time for the signal to arrive at the receiver. So in digital signal routing, the total length of the trace is going to determine how long it takes a signal to go from pin A to pin B. Within a parallel bus, meaning like a data bus or an address bus in our modern computer systems, right? So when we say we have a 64-bit operating system, that means our data bus is 64 bits wide. That means all 64 bits of data are intended to arrive from the memory chips to the processor at the same time, and so on. To match the timing of the signals within the bus, all traces need to be the same length within a given tolerance. Adding length to the shorter traces to equal the length of the longer traces achieves this the timing needs. And care must be taken with the height and gap of the trombone or serpentine area to ensure no excessive crosstalk. So both the height here and the gap between them needs to be of sufficient distance such that if I put these two close enough together, the signal going out on one is coming back on the other because it's going the same. It's all flowing this way right here. So it's going from left to right here and right to left here, which means I could potentially crosstalk to itself if they are long enough length or small enough gap here. So we need to ensure proper gap is met, as well as that the proper height here, that I don't make the height so high that I can cross couple into my adjacent traces and so on. So all these things need to be taken into account. A proper signal integrity analysis needs to be completed to ensure that that is taken into account. All right. Any questions on the topics I've covered today? again, we'll see more of this in practice on Wednesday or next week. So this week, we're really going to bring our parts forward into the layout if we haven't done it already. We're going to start working on the localized routing of the individual circuits and then getting the pre-routed sub-circuits placed into the board. So we probably won't get to serpentine routing, the actual serpentine or orthogonal routing and so on for a couple of weeks. But any questions on this before we call it a day here? Yes, question.
Yeah. So I actually have a question. It is exactly for this here layout example that you have, and in this example where you have the caps on the top layer, and then you have kind of a polygon which is then connecting the pads directly to vias. Is that something which is, let's say, how does this, let's say, it comply with this idea of doing thermal reliefs and or thermal ties, as we call them? Do we need to do some kind of calculation here as well, or is this kind of good enough that we?
So we're going to talk about this in significantly more discussion when we get to signal integrity. There is a reason for this, and we will, as I mentioned earlier today about like the heatsink, where your assembler does have the ability to put extra thermal energy in, just you would not be able to solder it by hand. There is a signal integrity reason for doing this, even though it is a little bit worse from a thermal point of view. It has to do with signal integrity and low inductance paths from the planar, from the physical caps down into the planar capacitance for our power distribution capacitances here. And I'm going to cover that in detail when we get to signal integrity discussion.
Okay, thanks.
But yes, I would agree with your assessment there that yes, if I do a solid area of copper right here, well, now I'm violating what I just said about, solderability. I was like, yeah, that is the case right there, but there is an overriding in modern digital design need from a signal integrity point of view, and we'll see why that is dealing with planar capacitance and low inductance paths for those planar capacitances and decoupling capacitors that will become the more dominant effect now compared to the thermal and the soldering effects. But great question. Any other questions before we call it a day? All right. Well, if there are no questions, I say I give you guys your 5 minutes back and we call it a day, and I will see everybody bright and early on Wednesday then.
Okay, thank you very much, Professor. Bye.
Right. Thanks. Bye.
Take care.
Thank you.
Cheers.